Hello, this is Mr. White, and this video is on Basic Differentiation Rules, Part 3, and we'll specifically be getting into free fall motion applications. In other words, objects falling to the Earth or whatever other celestial body we may pretend to be inhabiting, and they are only subjected to the force of gravity. So here's the one rather weighty exercise we're going to be going through, multi-part exercise. Pause and read it over if you like at this time. But before we get into the details of this specific exercise, let's just review real quickly the concept of free fall motion. So let's say our guy Justin is jumping off of buildings. I don't know why he would do that, but he looks a little confused in that picture anyway. And let's consider what we have got on our hands here with this graph. We've got a graph of position. And you may think of that as height if you prefer. And we're going to use the letter S in this class. You may use a different letter in physics class, but be flexible. We'll use the letter S. And let's say that we are using units of meters. And let's say the horizontal axis represents time. Time will be denoted by the letter T, and it will be measured in units of seconds. Okay, so let's be clear. We are not implying with this graph that Justin is jumping away from the building. We're not implying that he's landing 8 meters away from the building, because that is not 8 meters. That is 8 seconds, right? So is Justin landing away from the building? Is he? We don't know. We're not even weighing in on that. We're only focusing on his vertical height, S, as a function of time. We have not even made any statement or any comment on, is he falling away from the building, or is he just jumping straight up and falling vertically down alongside the building? We're not even weighing in on that at this time. All right, let's consider what can we tell from this picture. Let's consider first Justin's initial time and his initial position. So we're focusing on this point, of course, and that would be Justin's center of gravity that I'm noting at that point there. And it looks like his initial time, well by definition, his initial time is 0 seconds. That's where the stopwatch starts. And let's say that that's T subscript I for initial. We could also use T subscript 0. That's sometimes used. Not a big deal. I'm not too picky. And his initial position appears to be 10. I'm looking at the 10 meters along the vertical axis. So let's say that his initial position, S subscript I, or S subscript 0, I may use that in class sometime. Again, I don't have a strong preference. We could also say that that's S when you plug in 0. And we're saying that that appears to be 10 meters. So again, S sub 0, S sub I, S of 0, they're all the same thing. And what about the final time in his journey? And the final position? Well, according to our graph, it looks like his final time occurred at about 8 seconds or so. So let's say that T final, or T sub F, appears to be about 8 seconds. And let's say that therefore his final position, S subscript F, is going to equal S when I plug in 8 seconds. And what is his height when he's at the ground? Well, by definition, he's at 0 meters. He is 0 meters off the ground at the end of his trip there. What else might we be interested in? Well, sometime we're going to ask, I don't think it's asked in this exercise, but we may be interested at some point in what about this point up here, the maximum position. So what might we say about the time of his maximum position and the maximum position itself? According to this picture, it looks to be about 3-ish. And again, that's the time. So I might say T max equals 3 seconds. And it looks like his position is about 16-ish. So we'll say S max, which is the same as plugging in the T max, right? And these are all approximations. I'm just, again, going more for the concept here based on this picture. And in the actual exercise, we'll go into some more detailed mathematics. But make sure you got all those concepts straight. And as far as where does position really fit into all of this? I'm sorry, velocity fit into all of this? Well, think about that if you have meters along the vertical axis and seconds along the horizontal axis, if you were to take a rise over run, wouldn't that give you meters per second? So if you were to look at the slope right here, and if you were to take a rise, which is measured in meters, and a run, which is measured in seconds, wouldn't that give you meters per second? That's a pretty strong clue right there as to why the derivative of position gives us velocity, instantaneous velocity specifically. So let's shrink all this down, and let's get the last two concepts we'll go over before we get into this specific example or this specific exercise is instantaneous versus average velocity. We are recognizing that the instantaneous velocity, the slope at any given point, we are arguing is going to give us meters per second, which is going to give us the instantaneous velocity. And we see that that is changing at every point along this graph. We see that it was a positive slope along this stretch, which makes sense because a positive velocity would be consistent with Justin traveling upward, whereas the negative slopes over here are consistent with the idea that Justin has a negative velocity. He is falling downward. So those are the instantaneous velocities, and they change as a function of time, right? So we are going to say that, we will denote that by v of t. The fact that it's a function of t is what tells us that we're talking about instantaneous velocity, and we'll say that that is the derivative of position. And if you prefer, you can also say d over dt of s of t if you prefer. Multiple ways of writing all of this. Now, what about the average velocity? Average velocity may bring to mind the old d equals rt equation that you used back in little kid math. Think of r as being our average velocity. We're not going to use the letter r. We're going to use v for velocity. And d, think of d as being the difference in your initial versus final position. And t will still represent time, but really specifically change in time. So really notice the consistency here that if I were to rearrange that, I'm going to say that that old d equals rt is really, r represents our average velocity. T really represents delta t, a change in time. We're not talking about time in the absolute sense. And d really represents the change in position. That's what distance is. So if I were to rearrange that, I would get v average, or just rearrange that algebraically, equals delta s over delta t. And let me take a moment to emphasize a similar structure here, that up here I had what I could have just as well written. Here's another way just to write instantaneous velocity. Notice the similar structure of ds over dt, the instantaneous velocity, versus delta s over delta t. But they're similar in structure, but but they definitely are different quantities. The delta s, what's the total change in position? Well, if I scroll back up a little bit, if the initial position was 0, excuse me, that's time. If the initial position was 10 minus the final position of 0, that's my delta s. And likewise, my delta time will be 0 minus 8. So let's scroll back down here. And again, delta s really means s final minus s initial over t final minus t initial. And just a moment ago, I may have gotten that backwards. I may have a moment ago have implied initial minus final over initial minus final. And I hope you see that that's really will give us the same result. So excuse me for that little confusion there. But in this particular case, we're saying that his final position was 0 meters minus his initial position of 10 over a final time of, let's see, we said 8 seconds minus initial time of 0 seconds. That would give us negative 10 over 8, which is negative 5/4 meters per second. And how does that look graphically? This is the last point I'll make here. That negative 5/4 meters per second, where does that appear on our graph? Well, that just happens to be the slope of this secant, the secant slope. So again, instantaneous velocity represents slopes of tangent lines, whereas the average velocity is going to represent the slope of this secant line. So v average would be the slope of that, whereas any of these instantaneous velocities, those are given by the instantaneous b of t. Okay, so I hope that was a helpful instantaneous review of these concepts. Let's go ahead and apply that now to this example, this exercise. So let's take a look at this specific exercise. Justin is thrown upward from a 70-meter tall building with an initial velocity of 20 meters per second. We were just given this basic structure for a position function. Later on in integral calculus, we'll understand, we'll get some further insight as to why that equation is the way it is. But for now, we'll take it as a given. And then we're asked questions about the position and velocity functions, average velocity on a certain interval of time, the instantaneous velocities at both of those times, amount of time till Justin hits the ground, and his velocity upon impact. So let's just focus on part A. All right, so S of t, we're given the basic structure here, so this isn't going to be too difficult. V subscript 0, that's the initial velocity. Now maybe you might write it as V subscript I for initial, but V sub I, V sub F, I'm sorry, V sub I, V sub O, think of them as the same thing, initial velocity. And in this case, the initial velocity is told to be 20 meters per second. So plus 20 t, and the initial position. If he is starting atop a 70-meter tall building, if he's on top of that 70-meter tall building when time t equals 0, that's his initial position. So plus 70. And there is our position function. How am I going to get his velocity function? It is implied that if we're asked for a velocity function of time, that's implied to be instantaneous velocity. So even though it wasn't explicitly said, let's understand that that's referring to instantaneous velocity. And again, the word function really clues us into that it's a function of time. So b of t is really just the derivative of s of t. And if I apply my basic differentiation rules, my power and constant multiple rule on that, I will get negative 4.9 times 2, or negative 9.8 times t to the 1 power. The derivative of 20t, according to my basic rules, will be just 20. And the derivative of a constant is going to be just 0. So there are my velocity and position functions. All right, part B, determine J-Beeb's average velocity on the interval from 1 to 5. And I think here it would be helpful to really come up with a graph, a picture here. So let's do that, develop that real quickly. It doesn't have to be in a great amount of detail, but let's say here's Justin's position. We're graphing position. Starts at 70, and he starts out upward. So he's going to go up for a while and then come back down. So just like we saw on the previous slide, something like that. And let's say that at 1 second, let's say he's right here. And I don't really know whether he's still on the ascent or whether he's on the descent after 1 second. But let's just say that this is 1 second. And let's say 5 seconds is somewhere over here. Again, we're going more for the concept than a whole lot of accuracy here. So where is his average velocity going to be? Remember, average velocity, and the previous slide I said it was final position minus initial position over final time minus initial time. I guess I should amend that here. Since we're working on an interval from 1 to 5, I won't refer to these as initial and final times, but I will say that it's the position at 5 seconds minus the position at 1 second. And you know what, I'd actually like to really just capture, again, this as delta s over delta t. And remind yourself of the relationship between this and the d equals rt formula from the olden days, the little kid math days. So delta S really means S of 5 minus S of 1 in this case, over time t equals 5 minus t equals 1. So that's going to be our average velocity. Now where am I going to get S of 5 and S of 1? Well, it's a good thing I've got an equation here, isn't it? Obviously I could just use mental math or arithmetic on paper to do that. I'm going to go ahead and cheat a little bit here for time's sake and use the calculator. So I've already graphed this function in there. Again, I know that the function is really in terms of t, but I've typed it in there as x. That's understandable. I've got some reasonable window settings here. And let's go ahead and trace. If I trace to t equals 1, I see that the position is 85.1. So if I trace to t equals 5, I see that position is 47.5. Okay, so let me reflect that on my picture over here. This was 85.1. And this here was 47.5. All right. And so that gives me, let's see, 47.5 minus 85.1 over 5 minus 1. And that's going to give negative 37.6 over 4, which will in turn give me negative 9.4. And again, what are the units here? This is average velocity, so this was meters per second. And conceptually, do you see where that is on the graph? Where do we see negative 9.4 on the graph? It is the slope of this line right here, the secant slope, the secant line right here that goes through those 2 points. That has a slope of negative 9.4 meters per second. Now, the next question asks for us to determine Beebe's instantaneous velocity when t equals 1 and t equals 5. And at these 2 times, what is the instantaneous velocity? Before we jump into the calculations, let's look at the picture. I'm expecting an instantaneous velocity. It's kind of positive here. I did see when I pulled up the calculator that this was not a bad approximation for what this graph would look like. So I'm expecting that he's still going upward when t equals 1. And he's still going, and then he's going downward at t equals 5 quite quickly, presumably. So that's what I'm anticipating, and let's see if that actually plays out. We're going to use this answer from part A. We're going to use this velocity equation to answer part C. So I'll leave it so I can still see them both on the screen. So I can still see that equation just on the upper edge of the screen. And I'm going to write B of 1 equals negative 9.8 times 1 plus 20. And that's going to equal, let's see, 10.2, right? So after 1 second, remember he started out initially going 20 meters per second. After 1 second, he slowed down to 10.2 meters per second upward. But after 5 seconds, he's already peaked, and he's headed downward towards the Earth. And that would be at negative 9.8 times 5 plus 20 meters per second. And negative 9.8 times 5 is going to be negative 49 plus 20. That will give me negative 29 meters per second. And again, the negative is what denotes that he is going downward. So again, to repeat, those were the slopes 10.2 versus negative 29. And again, our average velocity had that secant slope right here. All right, we are now asked how long till the Beebe's knees splats on the ground, and finally part E, what is his velocity at that time when he does impact the Earth? So let's go back up just a little bit here, and where are we looking on the graph now? Let me get rid of some of these slopes here. And conceptually what we're looking for, as far as how long until he splats on the ground, we want to know what is the time at this point. We could tell it's going to be a little bit more than 5 seconds, right? So what is this time right here? And furthermore, what is his velocity when he hits the ground? That's asking us what is the tangent slope at that same point. Okay? So how are we going to figure that out? Well, if we want to know when he hits the ground, hitting the ground by definition means that that his position is 0. So that means that his position, his final position, is going to be 0. So what we're going to do is we're going to take that S of t equation and we're going to set it equal to 0 here. So TF for T final. And remember the position equation, if I scroll back up, was given up here. Negative 4.9 t squared plus 20t plus 70. So let me just repeat that down here. But I'm going to use t sub f to denote that that's a specific final time that I'm looking for. So negative 4.9 t sub f squared plus 20 t sub f plus 70 equals 0. And I just need to solve that as the quadratic equation that it is. So I can do the quadratic formula real quickly. And just for time's sake, I paused and just put it up there, just wrote it up there. And if I type that into the calculator, I see that I get either negative 2.25-ish or 6.34-ish. So let's write that. Again, negative 2.25-ish, or I'll say go ahead and go to another significant figure, or 6.336, and these are times in seconds, right? So we're not really interested, we're not time traveling here, we're not going back in time, so I'll cross out the negative value, although I will point out that graphically, if I go back to my graph here, notice that that is simply the time, if I were to continue this parabola back in time, that would be this time right here. But I'm not interested in that one. I'm only interested in this one over here. And that's what the 6.336 is. So that is our t sub f. And I will point out that if we allow ourselves to use graphical methods, I can bring the calculator up on the screen. And that's where I would go to second calc, and I would go to 0. Option number 2. I'll press the keypad number 2. And I do the whole left bound, right bound thing. I'm just going to type in 5 seconds and then 7 seconds. I'm cheating a little bit because I already have an idea of what the answer is, right? But I'll at least confirm that there I've got my 6.336. It agrees with my algebraic answer. Now, what's his velocity at that time? That's where we'll simply take that time and plug it into the velocity function. So if I scroll back up, here is where the velocity function was given, negative 9.8t plus 20. So let's just plug that in. So the velocity equals negative 9.8 times that time of 6.336 seconds plus 20. So back to the calculator, negative 9.8 times, that's the last answer I have in there, so I'll just do times answer plus 20. Negative 42.095. And what does that mean? That's his velocity. That's how fast he hits the ground. And that is in meters per second. And again, that is the slope of the tangent line at that time when Justin hits the ground. That's the slope of this line right here. So I know that was a bit of a lengthy, involved example, but hopefully that all made sense and you know what to do if you've got any questions.